in so in the folder, there's the thing that says like reaction rate, and you should have picked up a thing on your way in. There are five major things that affect the rate of a chemical reaction. Some reactions happen so quickly that they're like explosive. Other chemical reactions, take place over the course of weeks or months or years and can operate like really, really, really slowly. So sometimes it has everything to do with what chemicals you're reacting. So, like for instance, like dynamite or gunpowder, once that reaction starts, it's going to end really quick. There's nothing you're going to do to like really slow the reaction down or speed it up. It's a violent, fast reaction. Some other reactions, like the reactions we've done in the lab, they take place over the course of a few minutes. We kind of have them rigged so that, I mean, we don't want to blow the lab up, right? And you don't want the reaction to happen so quickly that you can't see what's happening during the reaction. We also don't set up lab experiments where like, you won't see a change for 5 hours because that's kind of dumb. You put the stuff together and you're looking and you're like, I don't think anything's happening. So part of the not really like it's a trick that we like trick you, but when I set up the experiment for you to do in the lab, it's kind of optimized to give you a good sense of what takes place during the reaction. But there are five major things that affect the rate of reaction. And some of these things are common sense. I'm going to give you real practical examples. And this picture in the top is like a spear point, and it's a Bronze Age spear point, and it has copper on the edge, but the copper also tarnishes. Like when you get a brand new penny, pennies are a good example. Pennies, they're pure copper on the outside. I don't know if you know this, but well, whenever we did the thing with the penny lab earlier in the year, the pre 1982 pennies, they're all copper. They're 100% copper. All pennies after 82, they're clad. And what it means to be clad is that there's a zinc planchet, and then what's around that is a copper cladding. So whenever you see a penny, it's actually 5% copper and it's 95% zinc. If you take a saw and you saw a penny in half, it's like mostly zinc with thin copper on the outside. It's kind of like when you ice a cake. It's mostly cake. There's a little bit of icing. When you look at the cake from the outside, you can't tell if it's vanilla or chocolate until you slice into it because all you see is the icing. But no matter what, if it's an old penny or a new penny, the outside is pure copper. And when pennies start out, they're nice and bright and shiny copper colored. But over time, they change. The copper becomes a little more dull. The copper changes to like, a dark brown color. If it gets in the presence of like salt, it can turn like black. Those are copper oxides. It's the oxygen in the air reacting with copper. But those reactions take place very slowly. It'd be really dumb if copper reacted very quickly with oxygen, because then like the metal would get destroyed quickly. So on the activity series, the metals that are way toward the bottom, the very inactive metals, in chemistry we actually call them coinage metals because they're metals that are like nickel, copper, gold, silver. Those are metals that are very non-reactive and they're very useful to make coins out of because like if you were to make a coin out of calcium and you put it into water, it would make a solution of calcium. The coin's gone. You've lost the value. So some reactions happen relatively slowly, but they happen. Um, what's a little tricky here? I don't know if I ever told you this. What's true about all pennies before 1982 is they're 100% copper. All pennies after 1982 are 50% or 5% copper, 95% zinc. But if you get a penny that's from 1982, that's the year they made the transition. Some of them are pure copper and some of them are copper and zinc. But what you'll find is that if you get pennies and change, you will rarely find pennies from before 1982 because coin collectors and numismatists have removed them all from circulation because they have a value in copper that exceeds a penny. It's about 4 cents. So and that's called the melt value, which doesn't literally mean that you melt the coin down, but if you find a coin in change from before 1982, it's worth about 4 cents. take it out of circulation and hold on to it. Just get a whole bunch of them. And you can trade numismatically in pre-82 pennies. You can go to a coin show with, a big bag of 1,000 pennies from before 1982, and you'll get 4 cents a piece for them all day long because that's what they're worth. Like, you just made money, but you got to dig through a lot of coins to find them. Similarly, all quarters from before 1962 are pure silver. They're worth like $6 a piece. If you get in your change a quarter from before 1962, it's just straight up worth about $6 in silver. But you won't find one because everybody's removed them. You know what I mean? Like, they're not just floating around. In fact, even banks remove them. They can figure out which ones they are. You got to look at the date, which is kind of a pain. So the things that affect rates of reaction. One thing is temperature. So here's what temperature is. Temperature measures how fast things move. So if you're trying to get chemicals to react with each other, and this goes in order. So like the thing you picked up is like guided notes, and these are the factors that are on it. One factor is temperature. The higher the temperature, the higher the reaction rate. So the deal is, in order to make chemicals react, if you've got chemical A and chemical B, as reactants, and you're trying to get these things to react, they have to physically touch and come into contact with each other. And if the temperature is low, like if it's cold, or if it's hot, so if this is like hot, the velocities are high, they're moving quickly, and there's a good opportunity for them to collide. But if they're cold, then they're just literally moving slow, and it takes more time for them to come into contact with each other. In order for reactions to take place, the higher the temperature, the higher the rate of reaction. The other reason why the rate of reaction increases with temperature is that in order to make some reactions happen, you have to just get it to a certain temperature. So like paper will react with oxygen and burn, but it doesn't do that at room temperature. Like if it's sitting at room temperature, it's not going to burn. There's a minimum temperature necessary to make the paper burn. But it's also true, like if you have a fire, like a wood stove, or even like if you're burning charcoal, if the temperature is low, the rate at which the burning happens is low. As the temperature goes up, you can get it to burn even faster, which makes the temperature rise even more. So the higher the temperature, the greater the amount of heat, the greater the rate of reaction. There are no good examples of chemical reactions that happen faster when it's cold. You increase the temperature, it's going to go faster. So a common thing that happens in chemical manufacturing, chemical plants, is oftentimes like the reactants are heated up. Heat that stuff up and you get the reaction to go faster. You can process chemicals more quickly. I think that might be common sense, but it's true. It's true with cooking. Like when you cook food, there are changes that happen physically, but there are changes that happen chemically. And the rate of those changes chemically are dependent upon temperature. There's a certain protein that is in carrots. And I don't know if you're one of these people, but I am, and so is my wife. Like raw carrots are delicious. They're crunchy, they taste great, they're refreshing. You cook a carrot, it makes me want to vomit. The flavor completely changes. And for some people, that's true. So if you're like most people like carrots taste the same if they're cooked or not cooked. They're just a little mushy when they're cooked. Well, you just don't taste that change in the chemical. But to me, a cooked carrot is the most vile thing on the planet. I would have to really be starving. I would have to be like, this is it. Only thing I got's carrots. I'm probably going to die today, so I guess I'm going to stomach them. The higher the temperature at which they're cooked, the greater that change happens. It's the same with corn. If corn is warm for a long time or is steamed for a long time, it also changes flavor a little bit. You know what I'm talking about? And the longer it's warmed up, the greater the temperature change. Those are proteins that become denatured. They're large proteins that break down into smaller chemicals, and those different chemicals have a different flavor. It's a chemical reaction that takes place within the food. The higher the temperature, the faster that reaction happens. Also, time plays a role too, because the longer it sits warm, the more that change takes place.
Is there any way, like, if you think of denatured enzyme that you can reform it?
Put it back together?
Yeah.
No, not really. I mean, the plant itself makes those proteins.
Right.
You know, it's taking like carbon dioxide and nitrogen and air and making those large chemicals. Um, and then whenever you heat it up, they break down. It makes it easier to digest. Like when you cook food, it makes it easier to digest. Um, like you can eat raw food. You can eat raw meat. You know, like I mean that's what the animal world does. Can you name any other animals that cook their food before they eat it? Like no, only humans cook their food before they eat it. The whole rest of the animal kingdom like just eats the food raw. But when you eat the food raw, the chemicals are larger and it's more difficult for your body to break down. A lot of it passes through undigested. When you cook the food, it partly changes the flavor, but it takes a lot of large molecules and breaks them down and makes them easier to digest. And it's usually tasty too, you know? But like the other practical reason to cook food is that in the animal kingdom, animals get sick and die all the time because they're
Pardon
eating
interruption. This is the final
like
interruption for
parasites,
this
bacteria,
is for seniors,
viruses.
any senior who brought in their picture packet to have their photo retaken or missed having their picture taken in the fall should report to the Commons this time. This is 12th grade students only. Thank you.
So like generally in food safety, once things are up to a certain temperature, you've killed off anything that can like also get you sick, right? So, but yeah, those changes take place at higher temperature. All right. Another thing, concentration. All these solutions that are aqueous, where you put ions in solution to make a chemical reaction, it depends upon the concentration. So let me tell you a little thing about this. So let's say you got 2 containers with water, and we're going to have a reaction take place where we've got some sodium ions and we got some chloride ions, and maybe we're going to have some barium ions and some sulfates. 2 minus. Barium's 2 plus. So in this chemical reaction, maybe we took sodium chloride, barium sulfate, we put them together, and the reaction that's going to occur is going to be between barium and sulfates. If the concentration is low, which means not many ions per volume, the reaction rate is going to be slower. But instead, what if we have the same container with the same amount of water, but we have way more, like we've got way more number of reactants. So let's say we have, 3 times as much reactant for each chemical. In order for the reaction to take place, if barium sulfate is going to be the product, we need to get those barium atoms and the sulfate ions together. SO4, 2 minus. I don't know, what else do I need? I need some more bariums. Here's another sulfate. So it turns out when you have a low concentration, and we haven't studied concentration yet, we will, concentration of solutions, there's ways to quantify the concentration of a solution. When the concentration is low, if we're trying to get bariums and sulfates to react, and they have a large mean distance between each other, the rate of reaction is lower. If instead, we really pack them in. Now here's a barium and a sulfate, they're right next to each other. Here's another barium and a sulfate right next to each other. Well, there's a barium and a sulfate, they're further apart. But the higher the concentration of solution, the faster the reaction becomes as well. When the solution is very dilute, the reaction rate slows down. So you can also vary the rate of reaction by varying the concentration. If you want the reaction to go slowly, lots and lots of water, not much chemical in it, the reaction goes slow. You want to get the reaction rate up, get a whole lot of the chemical in there very, very, very quickly. So the higher the concentration, the faster the reaction. So high concentration, we have a symbol for concentration. We have a fast reaction. So like the thing we did the reaction with baking soda and vinegar. Vinegar is usually 5% acetic acid. So what that means is if you have vinegar, it's 95% water and then 5% acetic acid. And then when you put the baking soda in there, the baking soda has to react with the vinegar, with the acetic acid itself, but there's a whole lot of water molecules around. You can buy acetic acid that's called glacial acetic acid. It's nearly 100%, well, it's not 100%, I think it's like 74% acetate ions in solution. And if you take concentrated acetic acid and put baking soda in, it's a very, very, very fast reaction. The carbon dioxide gas is created very, very quickly. It'll kind of make a mess. So the reason why vinegar is only 5% acetic acid, like you're buying 95% of the bottle's water and only 5% is the acid, is that if the acid concentration is significantly higher, it's really, really, really stinky. You'd be able to use less in a cleaning solution, or sometimes vinegar is used in cooking, like to make sauces and stuff. We've just settled in at 5%. That's like the typical concentration. That's where we're at. Same with rubbing alcohol, which is isopropyl alcohol. You can buy that at like 70% or like 90%. And that percent is the concentration. The rest of it is like just the water. So the higher the concentration, the faster the reaction. Surface area makes a difference. Okay, so if you have, let's say you've got a piece of copper, like a coin. So if this is like a piece of copper, and the copper itself is a nice flat piece that's nice and smooth, and that smooth piece has a particular amount of surface area. If instead you take and you slice that piece of copper so that now there's like smaller pieces, you've now increased the surface area because the piece of copper that was now in the middle is now separate in some kind of way. This total surface area is the external surface area of that. But if instead we take and we break this piece of copper up into lots and lots and lots of pieces, and all those little pieces all have lots of surface area, the total surface area has increased dramatically. So a large surface area, by grinding, ripping, tearing, cutting, increasing the amount of surface area for the same thing, makes the reaction rate go faster. In other words, if you're trying to get something to react, you need the contact area in order for the chemicals to come together. If it's going to be corrosion, if it's a copper penny, the oxygen only can react with the outside. If you grind it up to make like copper powder, the reaction is going to happen at a faster rate. In other words, more is going to react per amount of time. So like mortar and pestle, we'll have those available in the lab tomorrow. Mortar and pestle, it's like the bowl with the thing, you grind it around. That increases contact area and surface area. It's also related to making solutions. Whenever you take prescription medication, it can either be a solid pill, like a solid pill, and the solid pill, when it goes into your stomach, takes time to break down, and that's like called slow release. On the other hand, some prescription medication comes in a tablet that's like plastic or rubber, and inside there's a powder. And basically, as soon as that hits your stomach, the thing breaks open, and now it's a large surface area powder, and it's fast acting. It's going to get absorbed into your blood faster. That's not necessarily a chemical reaction, but the larger the surface area by grinding it up, the faster the rate ends up being. So increasing surface area, reactions need to be in contact with each other. More surface area, more area for contact, faster reaction. Another thing is about catalysts, catalysis. So a catalyst is a chemical that is present in a reaction but doesn't take part in the reaction itself. Generically, for all chemical reactions, catalysts play those roles where you have a reactant or reactants, and they make products. And catalysts are chemicals that in a chemical reaction, I showed you about this with the symbols for chemical reactions, where the catalyst is like written over the line for the reaction. It's a chemical that helps the reaction take place at all, but doesn't itself change during the reaction. And in biology class, you learned about enzymes. Enzymes are a class of catalysts which act to provide catalysis for biological reactions. So whenever there's a reaction within a biological system whose rate is controlled by a catalyst, that catalyst is called an enzyme. So an enzyme is a class of chemical that facilitates the rate of a reaction, but doesn't actually take part in the reaction itself. One example of a catalyst, and this is like a device where you hear that word, is in an automobile, you got like the engine up front, and that engine produces exhaust. And that exhaust goes out the tailpipe, like out into the air. In a chemical reaction in an automobile, you don't get to put just the fuel and oxygen in the cylinder. Instead, there's a lot of nitrogen that's in there because air is mostly nitrogen. So unfortunately, not only do you have like maybe octane, CH18 plus oxygen makes CO2 and H2O, but because the temperature of the reaction is so high and there happens to be nitrogen present, nitrogen and oxygen from the air also react to make nitric or nitrous oxides, generically NOx, which is not to be confused with nitrous oxide, which is used to increase oxygen concentration for the combustion itself. But oftentimes it's nitrogen dioxide or nitrogen trioxide. And the deal is, if these nitrogen compounds come out the tailpipe, those react with water vapor in the air to make nitric acid. And that nitric acid is not only a form of smog, that's like a light brownish colored smog in the air, but also the nitric acid rains down as acid rain. And increasing the concentration of acid in rain is detrimental to, like, open bodies of water. It causes, like paint to get ruined and stuff. So in automobiles, in the exhaust line, well, it doesn't hang down that far, it's not that big, there's a device called a catalytic converter. And that catalytic converter takes those nitrous oxide compounds and breaks them back down into nitrogen and oxygen. And what's inside the catalytic converter is either platinum or palladium. Palladium, is it PA or PD? PD. So it's either platinum or palladium. Platinum and palladium are both very, very expensive metals, and catalytic converters cost a lot of money. Once in a while, you might even read stories about a crime ring where people go around and cut catalytic converters out from underneath vehicles. Even a broken, busted up catalytic converter is worth hundreds of dollars. Sometimes people will go to like a car lot, even with brand new cars, usually with trucks, because they're like high up off the ground. They'll go to like a Ford dealership and cut all the catalytic converters out of F-250s, F-350s, and you can get $500 a piece for them at a scrapyard because they have a lot of metal in them. It's a big problem. It's kind of a big crime, and vehicle manufacturers have tried to do a better job of protecting the catalytic converter by putting it around a cage or a screen or something. There are aftermarket accessories like that. You can't put it inside the vehicle because it's like hot exhaust. You got to have that exhaust line outside and underneath the car. There's no way you could like hide that device. And it's ineffective if it's up in the engine compartment. It's necessary for it to be in line, so there's sufficient time for the gas to cool down a little bit. So I did have a car that had two catalytic converters, one just after the exhaust manifold and then one that was further back along. The platinum and palladium never get consumed. They never get used up. They don't take part in the reaction, but they're present to allow for the chemical to break down. So catalyzing reactions always increases the rate of reaction. And we're going to do problems where you see how like catalysts help rates of reaction. In the lab tomorrow, catalysis is not going to be a thing. But you'll see what we're going to do in the lab. Another thing is just stirring. So if in a reaction, here's an example. I'll use that sodium chloride and barium sulfate example again. if you have sodium ions maybe up here, and there's another sodium ion down here, and you got a chlorine and another chlorine here, and then there's like a barium, and then you got a sulfate down here, and there's another barium here, and a sulfate here. So if in this reaction where I've got a solution of sodium and chloride and barium and sulfate ions, if I'm trying to make a compound of barium sulfate where there's going to be a precipitate formed, maybe there's a barium and a sulfate here that's together, and these two react, form that solid, and the solid starts to settle down. But then up here, there's another barium and a sulfate, but they're separated. They're not physically in contact with each other. And I'm not saying that in a reaction, there's only going to be like 2 bariums or 2 sulfates, but if these reactants are held apart from each other, there's no way for them to react. So simply like stirring the solution, putting a stir rod in and stirring the thing up allows for the materials to come in contact with each other. So basically, if you want a chemical reaction to go fast, you want to like grind the stuff up to be a powder, react it at high temperature, keep it moving. If the reaction can be catalyzed by anything, use the catalyst, and I don't know, keep the concentration high. If you want the reaction to go slowly, protect the reactants from touching each other. Like the reason why you paint surfaces, like paint wood or put varnish on wood, is to keep oxygen from touching the wood because it causes the wood to rot. It also causes water to be infiltrated and gases to get into it. You paint metal, the oxygen can't touch the metal. You've provided a barrier to keep them from touching. If you also want to keep the reaction rate low, keep the stuff cold, keep the concentration low, don't stir it around, keep the stuff from touching. So those are the 5 major things that affect reaction rate. So here's what we're going to do tomorrow. We have Alka-Seltzer tablets, and Alka-Seltzer tablets themselves have calcium carbonate and citric acid. And when you buy an Alka-Seltzer tablet, it's a solid tablet. And both reactants are present in the tablet. But the tablet is stable for a really long time. In other words, the reaction doesn't really happen within the tablet. But there are things that you can do to make the tablet have a chemical reaction. And how Alka-Seltzer tablets work is you got to put them into water first. So by putting it in the water, that now creates a solution. But there are things that you can do relative to the quantity of water, the temperature of the water, and how the tablet is to start. Because when you buy the tablet, it's a solid, hunky tablet. Think about the things you can do to make the tablet react so that the chemicals that are within the tablet can react with each other in the least amount of time. In terms of like, could you heat it up or could you have warmer water? Could you stir the water? What about the quantity of water and the concentration? There is no catalyst for that reaction, but that's how that goes. There's chemical reactions that we make take place in our aquariums. I'll show you this one problem. Let me find a good one. This is an okay setup. Open image in new tab. Okay, back in the back left tank and in the fish room, we have these pieces of equipment. They're called calcium reactors. And how this device works is it actually is dead coral that you put inside this container. And this is a tank of carbon dioxide. You take carbon dioxide gas and pass it through this dead coral, and actually causes the coral to dissolve, and the dead coral that's dissolved then gets dosed into the aquariums, and live coral then like eats the dead coral, which is kind of like coral cannibalism, but it helps the living coral grow faster. And in order to make this reaction happen quickly, you can buy different sizes of this dead coral. You can buy big chunky stuff, or you can buy the real fine powder stuff. If you buy the big chunky stuff, the reaction happens slower. That's if you have like a fairly small aquarium and you don't need to put much calcium in. If you have a really big system like ours, well, not only do we have 3 of these calcium reactors, but I buy the really fine dead limestone, and then it reacts it much faster. The other trick is this carbon dioxide, whenever you bubble it into solution, the carbon dioxide goes in the bottom and it passes up through, and there's a little pump here, and this pump recirculates water. So by keeping the water recirculating within the reactor, and by injecting a lot of carbon dioxide, and by having the particle size be small, you get a faster reaction. Can't really heat it up because this water is at the same temperature as the aquarium water, because it's the aquarium water. So the reaction happens at whatever rate it does happen. But in the ocean, whenever coral reefs are at a low temperature, the rate of coral building and dead limestone deposition is slower. Whenever the water is really warm, the coral grows real fast. When the water gets too hot, the coral all dies. So that's a disappointing thing. This little pump here, this is actually the same brand of pump we use, these Camor doser pumps. It's a peristaltic dosing pump, and it has a tube here that doses the water at a certain rate by spinning, and it has a knob so you can adjust the rate at which the water flows through the reactor. So there's a valve up here where you can adjust the rate at the carbon dioxide. There's a pump here that adjusts the rate at which the water is added. These pumps can be interchanged to get different mixing rates, and you can change the size of the reactant. And that's how that works. So that's kind of interesting, because we have to replicate processes that happen in nature on the size of the whole ocean on in man-made equipment. This stuff's really expensive. That's partly why things are like crazy with saltwater. This little setup here, you got like, this is like about $1,500 worth of stuff. It's crazy, maybe more, because that's a carbon doser, probably $1,500. That's just to put dead coral in for the live coral so it can have a snack. All right, you can preview the Alka-Seltzer Rate Lab, but I'll give you a copy of it tomorrow. And if you're absent or remote, the lab will be like videoed and stuff so everybody can see it. What's up?
How exactly do catalysts lower the oxidation? Like manually, the enzyme itself